Hello, my name is Akshat Tangsale, and you're watching a recorded lecture video on vapor liquid equilibrium systems. The learning outcomes for this part of the unit is to perform vapor liquid equilibrium calculations in Aspen Plus, use the NIST thermodata engine to provide data comparison with experimental data against the model data, and to define activity coefficient and apply them in our calculations. So vapor liquid equilibrium systems are the most important systems in separation technology. It's used for separating molecules on the basis of their different boiling points and is used in gas absorption or stripping, distillation, humidification or dehumidification, evaporation and condensation, and requires understanding of the vapor liquid equilibrium systems. In this part, we will focus mainly on the vapor-liquid equilibrium of binary solutions, which means only two components. However, Aspen Plus can model multi-component systems as well, but we will leave that for later for more complex problems. First, we need to understand for simple systems like this how we can analyze the problem. To understand this, we need to look at the Raoult's law, which we will learn in more detail in CHE2162. Briefly, Raoult's law tells us that the partial pressure, which is equivalent to the mole fraction times total pressure of a system given by Dalton's law, must be equal to the mole fraction of that component in the liquid phase given by XA multiplied by the vapor pressure of that component at that given temperature, where vapor pressure is the property of the liquid, whereas obviously partial pressure is the amount of a component in the gas phase. So this equation relates the composition of liquid phase to the gas phase. Therefore, this equation is very important. This equation is normally applicable when XA is close to 1, which means you have pure A or close to pure A. If the components are similar in nature, for example, two hydrocarbons, then XA does not matter. The Raoult's law will be applicable for most compositions of the two systems. Henry's law, however, is another equation which relates the mole fraction of liquid to the mole fraction of vapor. Here it says that the partial pressure of a component in the gas phase which is equivalent to mole fraction times total pressure of that system is equal to the mole fraction of that component in the liquid phase given by XA multiplied by the Henry's constant HA at that temperature. The Henry's constant are tabulated in various data tables and can be found in reference texts like Paris Chemical Engineer's Handbook. Typically, in Henry's law, XA is close to zero, that is dilute solutions of A. Typically, Henry's law is applicable for gas solutions in liquids. So often this is used for gas absorption problems like carbon dioxide absorption in water, for example. So the fraction of carbon dioxide that is dissolved in water is very, very small. We need to be careful when applying Henry's law that the molecule does not dissociate, and when it absorbs in water or other solvents, it does not ionize and it does not react with that liquid. So carbon dioxide is not a good example because carbon dioxide dissolution in water actually forms a carbonic acid. Looking at vapor liquid equilibrium diagrams, so on the right hand side here it's showing a TXY diagram, so temperature plotted against X and Y compositions on the x-axis. These diagrams are shown for the more volatile component in the binary system. So in this diagram it's showing data for benzene toluene mixture, where on the x-axis it's only plotting mole fraction of benzene, which is the more volatile component in the benzene toluene system. This table or this chart is given at a constant pressure, which is in this case 1 atmosphere. The curve below on the bottom here shows the liquid equilibrium curve, whereas the curve on the top shows the vapor equilibrium curve. So to understand this, I'll show you some cartoons. So on point A, which is 75 degrees Celsius, and the composition of benzene is 0.5 mole fraction. So it's equimolar composition of benzene and toluene. Uh, Imagine we have a cylinder with a piston which is freely movable, which means the pressure is constant, and we have a completely cooled liquid. So this is well below the boiling point. Again, we will learn vapor liquid equilibrium in greater detail in CHE2162, but this is a condensed version of that. So if we start heating this, at some point we will reach the boiling point of that mixture, and all the curves, all the points on the curve here in the liquid curve are different bubble point or boiling point temperatures for that liquid. So at point B, we are seeing the first points of vapor coming up from the liquid phase, and um, the first vapors that come out of the liquid phase will be more concentrated in benzene. So the line joining the two, which is called as the tie line, the line joining vapor curve to the liquid curve, is called as the tie line, and the point at which it meets the vapor side of the curve gives the composition of the vapor. So as you can see, the liquid has a composition of 0.5 benzene, but the vapor has a composition of more than 0.7 mole fraction of benzene. So more volatile component will be enriched into the gas phase initially. If we keep boiling it, let's say some point at 95 degrees Celsius, the liquid will get depleted in benzene. So this time we have a benzene composition of only 0.4 and toluene is zero point 0.6. So as you can see, the liquid is getting enriched in toluene and vapor is getting enriched in benzene. So benzene mole fraction here is over 0.6, which is more than what we had to start with. So we are able to get two different compositions for vapor and liquid. If we keep heating it further, we reach the dew point curve or the vapor curve. At this point, most of the liquid has been evaporated. We have only last drops of liquid remaining, and therefore the composition in the gas phase is nearly the same as what we started with, which is zero point 0.5 mole fraction of benzene. Whereas in the liquid phase, even though we have only small few droplets of the liquid remaining, it will be quite a bit enriched in toluene, which means the benzene composition is quite small. As you can see, it's just under zero point 0.3 now. And if we keep heating it further, we have evaporated all of the liquid, and now we have completely vapor phase. And of course, the composition is going to be the same as we started off. So the curve has gone all the way from a completely cooled liquid, subcooled liquid, to vapor liquid equilibrium between the vapor and liquid curves. And then above the curve, we have superheated vapor. To be able to calculate the composition of the vapor and the liquid coming out of phase separator, we can use what is called a equation for the partitioning coefficient. So in this equation, the mole fraction of the gas phase given by Yi is equal to the mole fraction of that component in the liquid phase, which is given by Xi, multiplied by the partitioning coefficient Ki. The partitioning coefficient can be experimentally predicted or calculated, or can be thermodynamically predicted. So we will look at the equation for thermodynamics later, but let's say from experiments we know what Ki value is. We should be able to calculate the composition of both the gas phase and the liquid phase if we know the conditions. So to calculate that, we look at the multi-component system now, and we know in the gas phase sum of all the components will be equal to 1, and we know in the liquid phase sum of all the component mole fractions will be equal to 1. So if we subtract these two, we should get 0. 1 minus 1 should be 0. Um, in place of yi, we can replace now the previous equation, which was yi equal to kixi. So if we replace that, we get sum of all components for kixi product minus sum of all components for xi equal to 0. we can take xi common, and we can say ki minus 1 times xi equals to 0. That gives us the first equation. This equation can be simultaneously solved with the mass balance equation to give us the equilibrium equation. Let's have a look. So if we look at the mass balance for the more volatile component, so Zi would be the mole fraction of the feed multiplied by the feed flow rate, should be equal to the component mole fraction in the gas phase multiplied by the vapor flow rate plus the component mole fraction in the liquid phase multiplied by the liquid mole flow rate. And the second equation that we need is the total mass mole balance equation. So the feed will be equal to vapor plus liquid because it's non-reactive, so moles will be conserved. If we divide this whole equation by f and then define a new term which is nu prime, the Greek letter nu, it gives us the fraction of the feed that vaporized, which means v nu prime is equal to v over f, where f is the feed and v is the vapor flow rate. If we rearrange this equation, we can get xi equals to zi over 1 plus ki minus 1 times nu. So we get our second equation, which is a mass balance equation, and previously we had the equilibrium equation. If we combine those two, we can get this equation here, which is ki minus 1 times zi over 1 plus ki minus 1 times nu. If we add this for all components, we should get 0. And that gives us the Rachford-Rice equation. We can use this equation to solve for the vapor liquid equilibrium and get the component mole fractions in both liquid phase and gas phase. So let's have a look at an example. We have a mixture of propane, N-butane, N-pentane, and N-octane at 180 degrees Fahrenheit and 70 psia, which is uh, pound per square inch absolute. The K values are given below, so this must be from some experimental data or some theoretical prediction. We can use the goal-seek function to calculate both X and Y composition. So let's have a look how we can do that. So here I've set up a spreadsheet where I've already tabulated the components and the K values and the feed composition that is given to us in the problem in terms of mole fraction. This is the equation that we are going to use, and now we can have a look at how we can set this up. So we can solve for f of v, which is this function of the Rachford-Rice equation, and from that equation, if we start setting it up for each component, that is in this case we're setting it up for propane, so k of propane minus 1 times z of propane, dividing that by 1 plus ki minus 1 times nu. Here nu is unknown when we are going to solve for nu very soon. So we copy the same equation for all the components, and then we need to sum this, and our sum should be equal to 0 if we have to solve this problem. Of course, we get an answer of 0.67, so we can use the goal-seek function and set that cell to 0 by changing the cell nu. We get value very close to 0, which is minus 8 into minus 6. It's not exactly 0, so let's do the same trick as we did previously and multiply this number with a large number like a million. And in this cell, then we can equate this cell to 0 in goal-seek by changing the nu value, and there will be a small change in the nu value, and you can see that the function has gone even smaller. It's 10 to minus 12 now. To get the xi value, now we set up the xi function, which is divided by 1 plus ki minus 1 times nu. So this time we have the nu value that we know, and Therefore, we can lock that in, and we can copy all of this over, and then for yi we can get from the equilibrium problem, which is xi times the k value. So that gives us the yi value, and again we can copy this function to rest of the components. To check whether our answer is correct, we can sum all the xi values and see if it goes to 1. So that is an independent equation from the other equations. So we see that we get 1, and likewise if we do it for yi, we should get 1, because if xi sum is 1, yi sum should also give us 1. So that solves for the components using Excel. But so far we have been given the ki value, and in most cases we may not know it easily, or will be very difficult to experimentally establish. So we can use some thermodynamic predictions. This is a little bit beyond the scope of the unit and will be covered in third year when you do the chemical thermodynamics. But briefly, ki can be predicted by this equation, which gives us the lambda I times FIO, which is fugacity, divided by the fugacity coefficient multiplied by P, where this lambda is the activity coefficient. This is important to know. The activity coefficient is interaction between the molecules that are in the mixture. Fugacity is a new term that you may not have heard of before, and it's beyond again the scope of this unit to explain what fugacity is. You really have to go and study the chemical thermodynamics to be able to fully establish what fugacity is and what fugacity coefficient is. In short, if we know fugacity and fugacity coefficient, which are also can be calculated using first principles, we should be able to calculate the ki value. In Aspen, these parameters are built into the properties method. So in addition to the equation of state, there are activity coefficients which are built into the properties method, and therefore we need to choose a right property method depending upon the components we have. So the activity coefficient depends upon chemicals involved and their symmetry, their force of attraction, like Walter-Waltz forces, and their electric dipoles. Like chemicals like water will have a very high electric dipole, so polar components. If there are non-polar components, then their electric dipole is smaller. So in Aspen Plus, we can choose a correct property method to know how to choose a correct activity coefficient model, or to correctly choose a property method. You should look at the previous lecture on equations of state. In this section, we are going to see how we can use NRTL, UNIQUAC, and Wilson models to predict the property for components that we have. Both NRTL and UNIQUAC can model azeotropes. So azeotropes are systems where the composition in the liquid phase is equal to the composition in the vapor phase, which means we cannot separate them using the vapor liquid equilibrium. So distillation type problems reach kind of an equilibrium where beyond that you cannot get separation. So azeotropes are not good when it comes to separation. Which other way of thinking about azeotropes is that the the partitioning coefficient will be equal to 1. Ideally, we want the partitioning coefficient to be much greater than 1. So here, if we use NRTL and UNIQUAC, it can model azeotropes where we have two liquid phases. The two liquid phases do not mix together, so they're immiscible liquids. Whereas Wilson's method can only model azeotropes where we have only one liquid phase. So there's a NRTL and UNIQUAC are more advanced versions, so to speak. Moreover, activity coefficient also depends upon the liquid mole fraction. So therefore, the Ki, or the partitioning coefficient, also depends upon the liquid mole fraction. In such a scenario, the problem that we did earlier in Excel becomes an iterative problem. So we'll have to several times solve the Rachford-4-Rice equation to get the composition of the liquid and the vapor phase. So it becomes really complex if activity coefficients have to be incorporated into our Excel modeling. So the best thing is to do it in Aspen Plus, and here we look at the same problem that we did before. Again, we have propane, butane, pentane, and octane at temperatures of 180 degrees Fahrenheit and 70 psia. And this time the K values will be found from the Aspen Plus simulation. So setting up an Aspen simulation, we start off by clicking on File and then click New to open a new file. So I'm going to use a template for English units, which is uh, in now we know them as American engineering units, but English units were the originators for American engineering system. So here we select all the components that we want: propane, butane, and pentane, and octane. Once we have added all the components, we can select our property method. In the specification for the methods, NRTL has been already selected because I chose the template. We can add other methods like Peng-Robinson, and then if we click on Peng-Robinson in the binary interaction, we can get all the binary interaction coefficients. So if we go to the simulation of this thing, we can add a flash operator. So and then we need to define the feed stream for the flash operator and the product stream for liquid and the product stream for the gas. Then we can enter the temperature and the pressure at which the flash was operating: 180 degrees Fahrenheit and 70 psia. Once we have set that up, we can then define the stream. So let's take a basis of 1 pound mole per hour and then define the mole composition. So if we select mole frac in this and then enter the mole fractions that have been given to us: zero point 0.1 for propane, 0.2 for N-butane, 0.3 for N-butane rather, 0.4 for N-pentane, and 0.2 for N-octane. We need to also define the temperature, so let's just select the same temperature as the flash operator and the same pressure. The flash is just going to separate the phases. So if we run the simulation now and we look at the results, in the result summary, go to streams. This shows us the mole flow rates, and of course mole flow rates for each stream will not add up to 1. The total for both streams of S2 and S3 should be equal to 1. However, it does show us the fraction that vaporized, which is 0.1412. To get the mole fractions for both the streams, we can go to the custom stream table and see if we have it. If we don't, then we need to add a new custom stream, and then in the edit view function that we have looked at before, select the property and add the mole fraction to the selected properties. And now if we scroll down, we should be able to see the component mole fractions for both liquid and vapor phase. As you can see, these component fractions are not the same as the Excel one. Okay, if we compare the two answers, we can see that propane is 0.036, whereas Excel predicted only 0.028. Likewise, others are slightly different as well. So the slight difference between the Excel answer and the Aspen Plus answer is because of the activity coefficients, which were not built into the Excel simulation that we had. And of course, because activity coefficient also affects the K value, then naturally the K values that we were given will be affected as well. So far we have looked at the K values that the thermodynamics tells us. Okay, however, we need to be able to make this decision. Okay, our results are as good as the models that we choose, so we have to decide which model to choose. Therefore, we can sometimes check if we don't know, if we have a confusion between, let's say, whether to use NRTL or Wilson, then we can plot the model VLE data, vapor liquid equilibrium data, against the experimental data and compare to see which model comes close to the experimental value. So to do that, we have a worked example here again. We have water ethanol mixture, which is a non-ideal liquid mixture because water and methanol mix together very well in the liquid phase, and their molar volume is less than the sum of the molar volumes of the two liquids. At the same time, the activity coefficients are important because water is polar component. Ethanol is slightly polar as well, but water is more polar. So we need to see how we can use the proper property method. Here we are going to use Aspen Plus to generate an XY plot uh, for both ideal Wilson's and NRTL equation of states and compare them against the experimental data. So to do that, we start off by again selecting a new method. This time I'm going to choose metric units and enter the two components, so ethanol and water. Once we have added that, we can select the right method. So because my template already had an RTL method, that's selected. If we click on NRTL in the binary interaction tab, we get the activity coefficients for NRTL. Then we can choose Wilson's, and again if we click on Wilson's in the binary interaction, we get the activity coefficients, binary interaction parameters for those. If we go to binary method, which is on the top, and select the method that we want, we should be able to study them. We need to add ideal as our third comparison as well. So let's select ideal equation of state as one of the methods. Because ideal equation of state does not have any binary interaction parameter, we don't need to go there. So in the binary analysis, we select the vapor liquid system and we select ideal and generate the results. Then we can copy the mole fraction of ethanol in the liquid phase. So just select all and then press Ctrl C. It should copy it, and I'm going to copy it over to Excel so that we can plot everything together. So I'm going to give this a heading of ideal and plot X, copy X rather, and the X values can be pasted using Ctrl V, and then I'm going to select the vapor mole fraction of ethanol and then copy and paste in the spreadsheet. Then I'm going to use the second binary uh, input, where again I've chosen vapor liquid phase, property method of Wilson, and then run analysis. So as you can see, it gives a very different looking curve. Once again, to compare and put it on the same spreadsheet, I'm going to copy the liquid mole fractions of ethanol first, and then label this as Wilson, and then for X I'm going to paste, and then going back to Aspen, looking at vapor mole fractions of ethanol, copy and then paste in the Excel spreadsheet. Finally, we can set this up for an RTL method as well, and then going back to Aspen, we select a new binary method, choose NRTL as the property method, and then run analysis. And then if you look at the results, we copy the mole fraction of ethanol in the liquid phase first, and then paste it, and then vapor phase mole fractions for ethanol. So now that we have copied all the data, we can start comparing all of them against experimental data. So I'm going to pick experimental data from literature from Perry's Chemical Engineer's Handbook. So this I've pulled out from library, which gives Perry's Chemical Engineer's Handbook, and here we are going to plot the X. So copy and paste, and then also copy and paste the Y data onto the Excel spreadsheet. So now we have three model methods and one experimental data, and then we can start generating our plot. So we select data, and I'm going to add the X value of the experimental data first, name it as experimental, and then plot it against Y. So this is giving us the XY plot. Next we can plot the ideal gas values for X against Y. As you can see, the ideal gas does not predict the experimental value at all. So now I've added Wilson as well to the plot, and finally add NRTL model values to the same data plot. Okay, if we change the dots into curves to have a look at them, um, to distinguish between the dots for the experimental. So I'm getting rid of the bullets and then adding a line instead for all the model values, and keep the bullet points only for the experimental data. So as we can see, the Wilson and NRTL, they come close to predicting the experimental data. However, um, ideal gas equation of state is far beyond the prediction. And for us in this case, it looks like Wilson gives us a better prediction ever so slightly. There's only a small difference in the region, in the zero point 0.5 mole fraction region for ethanol. It deviates around from between zero point 0.2 to zero point 0.6. Other data points are well predicted by Wilson and NRTL both. So both, it looks like both NRTL and Wilson will give us a relatively good answer. Finally, to see if we can retrieve the data itself from the experimental data, that is from Aspen Plus. So here we have a screen capture of how to retrieve NIST data. So instead of checking Perry's Chemical Engineer's Handbook, we can just use this. So I'm opening the previously opened file, or methanol water vapor liquid equilibrium. Let's close the previously opened analysis, and go at the top here to click on NIST, and here select components that we want, ethanol and water, and click on retrieve data. It will take a few seconds or few minutes to retrieve the data depending upon the internet connection. So now that it has retrieved all the experimental data, we can see that for binary VLE in isobaric region, we have several data, experimental data given to us. In this case, I'm going to use the binary VLE 085 data because the pressure matches very close to the pressure that we were given. First, we need to check the consistency of the experimental data, whether it makes sense or not. So click on consistency tab on the top and then click on run consistency test at the bottom of the page. Again, it will take a few minutes to do the analysis. Okay, the analysis has been complete. Now we select the method that we wanted, the data that we wanted, 085, and click on Harrington graph, and looks like the graph is very well matching the data points. And we can also look at the Van Ness diagram, which also looks like it's a pretty good match. So it looks like the data is consistent, and therefore we can select this experimental data. The reference for that data is given at the bottom, so in case you want to look at that paper, you can use library to find that journal article. So we copy the temperature, we copy the mole fraction in the liquid phase for ethanol, and we can copy the mole fraction of vapor for ethanol. Okay. And then going back to our previous analysis that we had done for NRTL method, we can run the analysis at a slightly different pressure which the experimental data is given at, and go to the results of this. To copy the temperature, we need to first convert this into Kelvin. Select all, and then we paste the the model data for NRTL, and then we can copy the mole fraction for the liquid phase. So this is X for NRTL, and finally the vapor mole fractions for ethanol, and label that as Y for NRTL. So like before, if we plot it in a scattered plot, we select data, and in the x-axis, so let's label the series first. So txy data, so data means experimental data, and in the x values we are going to select the x values here, and in the y values we're going to select the temperature. Then we're going to plot ty data, and in the x values we select the y mole fractions, and in the y values for the graph select the temperature. So that gives us the txy for experimental data. Likewise, we can use it for NRTL, so tx for NRTL, and then in the x values for the graph we choose x mole fractions, and in the y values we choose the temperature. Click OK, and then set up the ty value for NRTL, and in the x values select the y mole fractions, and in the y value for the graph select the temperature. That should complete our graph. Once again, I'm going to change the the scale first, and then for experimental data leave the bullet points, and for the model data we're going to use solid lines. Okay, so here we can see that the NRTL predicts pretty well, but it does deviate a little bit on the low molecular weight, no molecular fractions in the gas phase for ethanol. It predicts the liquid curve very well. It deviates only slightly, but the gas phase deviates a little bit more. So that concludes the lecture for vapor liquid systems and how to analyze vapor liquid systems for flash operation in Aspen Plus as well as in Excel, and to retrieve data or to compare our model against experimental data in Aspen Plus. We are going to practice this a bit more in Friday tutorial. So I hope you do the work problems in this lecture at your own time, and then come prepared for Friday's tutorial.